So today we're going to be looking at the skeletal system. The skeletal system functions, first thing we'll cover here, we divide the functions or roles of the skeletal system really into two different categories. The structural function of the skeletal system and then the physiological functions of the skeletal system. So under structural functions, the main thing is that it gives a supporting framework for the body. Tend to think of our body being built around our skeleton. Some animals have an exoskeleton and everything's kind of built up on the inside of it with an outer framework, and we have an internal skeleton. Sometimes it's referred to as an endoskeleton when the skeleton is inside the body. But anyway, we have a supporting framework on which we support. All of our muscles and our organs are suspended and so forth. Next, I'm going to put in here movement or leverage. So our part of that supporting framework connects to our muscular system, and our muscular system helps us to move around. So movement is part of that. Leverage, whenever you're trying to push against something or just open a jar or something of that sort, we need to have a skeletal system there to provide the structural and force we need to do that movement. So movement or leverage is another important part of that structural framework function. Next, kind of a protective role, if we have kind of an internal armor. To protect internal organs. So mainly we think of our skull when we think of this function here, protecting our brain there, but we also have a rib cage around our heart and lungs, our pelvic bones do some protection of the lower abdominal region, pelvic region of the body. So anyway, our vertebrae encase our spinal cord. Those are things associated with protective roles of our skeletal system. So we have a supporting framework that allows movement and protection. Next, physiological functions. One of the first physiological functions we want to recognize is blood cell production. Before we have a skeletal system in our embryonic development, there are other tissues that are producing some of our blood cells. Liver, spleen, and some other locations in the embryonic body. But as our bones begin to form, they soon adopt that role of blood cell production. Another name for blood cell production is hemopoiesis or hematopoiesis. Hemopoiesis or hematopoiesis, blood cell production. Another role is mineral storage, I guess we'll call it. We have what we call bone salts in our bones. These are calcium and phosphate primarily, but anyway, there's a mineral structure. That hard material of the bone stores minerals, and we can retrieve that material from our bone. There's a way of getting that back. So mineral storage is another function there. And then finally, triglyceride storage. We more often refer to it simply as fat storage, but there are fat cells in the marrow of our long bones. Not all of our bones have that fat store in them, but some of them do. So triglyceride storage, the storage of fat, in what we call yellow marrow. Fat storing marrow in our long bones. So those are 3 physiological functions. So we've seen a total of 6 functions, 3 structural functions and 3 physiological functions. Oh, the next topic I don't think is all that important, but most textbooks include this information, so at least you'll be familiar with it. You've heard of it before. Bone shapes. We often can classify our bones into these different bone-shaped groups, but otherwise it's not all that useful information to us. Long bones, those that are like in our arms and legs and fingers, and our hands, the metacarpals, metatarsals in our feet. So those are long bones. Short bones, more like our wrist bones and ankle bones that are about as long as they are wide. They're more cuboidal in shape. Flat bones, flat is obvious, but our sternum is a flat bone, a good example of a flat bone. The scapulae on the back, are the shoulder blades, are flat bones. The bones that encase the cranium, or the skull, I should say encase the brain, bones of the skull, are flat bones. Sesamoid is an irregular seed-shaped bone, so it's shaped kind of oval-like or egg-shaped kind of seeds. Sesamoid, you think of sesame seeds. So seed-shaped bones, common in some of the tendons where we don't really name the bones, but they get caught up in there. Then irregular bones, kind of a catch-all for anything that doesn't fit in one of the other categories. So again, nothing cut and dried about this information, and not all that useful. Now, an important thing for us all to know in anatomy is the anatomy of a long bone. So we're going to make a drawing here, and I'm going to try to get everything in different colors and so on to make a nice illustration of a long bone. So let's start here with the bones, kind of like the humerus, so we'll just kind of give it some kind of shape. Here to give you the overall view of a long bone. Now on the very outside of your bone, there's going to be a layer of connective tissue, a dense, irregular connective tissue. It's a very, very thin layer of connective tissue around the outside of the bone. We call it the periosteum. The periosteum, I'm not going to put it right on the very end, that articulating end of the bone, but around the rest of the outside of the bone here, if I can do that without erasing my brown line. Here I'm doing this in a pink color. So this is on the outside of the bone, adhering to the surface of the bone. So that's the periosteum there. We'll go back and label that here in a minute. There's a layer of compact bone around the outside of the bone. So it's fairly thick along the main shaft of the long bone. So on the outside of the bone, pretty well all the way around, we have this thick layer of compact bone, which we talked about when we talked about histology earlier. We'll revisit that here in a little bit. But anyway, to the inside of the compact bone, we have what we call spongy bone. So I'm going to draw this spongy bone in here. There's a bunch of cross-hatched squiggly lines in there. Now that spongy bone pretty much fills up the end of the bone here and the end of the bone down over on this end here. We want to leave room for the epiphyseal line through here, so we'll put some more spongy bone down on the other side of the epiphyseal line. But beyond that, there's going to be a marrow cavity in the center, so there's no spongy bone in this marrow cavity to the middle. So along the edge, we're going to have some spongy bone just to the inside of that compact bone. Got to leave my epiphyseal line down on this end as well. And then put my spongy bone to the inside of my compact bone on this side. Now there's a region of cartilage that forms a cap on the articulating ends of the bone. We call it articular cartilage. Articular cartilage, and this is where the joint contact is made between one bone and the next bone. So we have articular cartilages at the ends. Let's start labeling some of this now. We just mentioned articular cartilage. On the ends, then this pink line on the outside here was our periosteum. Periosteal layer. Underneath of that we have the compact bone. Then our spongy bone. And in the middle is our marrow cavity. I left this line in here between spongy bone parts there that we call the epiphyseal line. It's the line of bone growth that's originally cartilage, and the cartilage continues to push out on either side to grow the length of the bone. The bone is constantly being remodeled and reshaped, but that's where we get the increase in bone length in a long bone, not in all bones, but in long bones. That's the way things grow. Let's see, next, I want to indicate some zones or regions of the long bone. The ends are referred to as epiphyses, so this is an epiphysis over here. That end right there, and this end down here would also be an epiphysis. The main middle shaft of the bone, the length of the bone here in the center, is referred to as a diaphysis. And that region from the about the epiphyseal plate into the main shaft here, it's a very narrow zone right in here. We often refer to as a metaphysis. So there's one there and there's one over here. So those are the main features of a long bone. Articular cartilages, there's one at this end as well down here. Periosteum that surrounds the main part of the bone where there's not a articular cartilage. Compact bone covering most of the entire structure, giving strength to it, and then spongy bone to the inside of that, and that's where we have our red marrow and blood cell production. Then the marrow cavity in the middle, remember that contains fat. That's where we store our fat in there, the triglycerides. Then the epiphyseal line down here, the area of bone growth. So there's the anatomy of a long bone. Now we're going to talk about some bone surface features. We'll be using this terminology quite a bit when we look at structures in laboratory of the human skeleton. But anyway, we're just going to go over this list of terms to give brief explanations of what they are. Many of them are self-explanatory, like a fissure. We all know what a fissure in the Earth's crust is, like it's a gap or a crack in the Earth's surface. So in the bone, if there's a gap, a space between two bones possibly, just a narrow gap between two sides of bony features, we can refer to that as a fissure. Next, foramen. Foramen, I often say foramen instead of foramen, but it should be foramen, I guess. The round holes that are in a bone. Often there's a nerve or a blood vessel that has to pass through a bone, and there's a nice round opening for that to pass through. We refer to it as a foramen. If there are a bunch of small holes in a particular location, we sometimes refer to those as foramina. Foramina. So these are all different kinds of holes. Next one, the fossa is not really a hole through the bone, but a depression in the bone, usually kind of a bowl shape or a shallowed out part of a bone. We can refer to as a fossa. A sulcus is more of a groove along the bone surface, kind of like a fossa, but being linear and going along a length. We refer to that as a sulcus. Next, meatus is another name for an opening in a bone, but not used quite as often as foramen, and we usually just think of that in terms of the opening for the ears, the auditory meatus on the outside. But anyway, it's another kind of hole that we're going to see pass through the bone material. Often these are, well, not necessarily, but sometimes longer, elongated, tubular holes through the bone. So, fissure, foramen, foramina, fossa, sulcus, and meatus. These are openings in the bone, or depressions, or concavities in the bone. These others are going to be things that stick out from the surface more. The term process, there are many things that are considered processes that go by other names other than process. For example, a tubercle. It's another kind of a process that sticks out from a bone. It's a small bump or a projection from the bone. Trochanter is a larger kind of projection from the surface of the bone. A crest, an elongated surface along the bone, sticks out. A line is a narrow, elongated structure along the surface of the bone that sticks out, usually not as much as a crest, not prominent like a crest. Next, tuberosity, just another term similar to maybe a trochanter or something, but anyway, it's a process, a projection from the bone that muscles attach to. Most of these are present to allow the attachment of muscle for the movement of your skeletal system, the movement of the body. So, process, tubercle, trochanter, crest, line, tuberosity. All different kinds of projections from the bone. And we'll see a number of different structures with specific names, the greater and lesser trochanter, the iliac crest. So anyway, those are things that stick out from the bone. Now, two more terms I want to add to this. Condyle is a term that refers to a surface, usually a rounded end of a bone, where you make contact with another bone. It's at a joint surface. These are usually smooth, covered with articular cartilage, where the two bones make their connection. So those smooth, rounded surfaces that form a joint are often referred to as condyles. Another kind of joint connection is referred to as a facet, F-A-C-E-T, a facet. These are usually smaller connections between two bones, still a synovial kind of joint, a freely movable joint, but it's more of a contact place where two places make contact more than a place where there's a whole lot of movement going on. These are usually smaller and nearly flat in their structure. Just a place where two bones meet and have a synovial connection, a movable connection. So these are different kinds of bone surface features, different kinds of holes or depressions, different kinds of projections or processes, and then things associated with joints, connections of bones. Bone matrix composition. Bone matrix composition. What is the bone matrix made of? First of all, H2O, water is part of it. Then collagen is a considerable portion of it. And then something we call bone salts. Mostly what we know as hydroxyapatite. Let me write that down underneath here. Hydroxyapatite. The relative amount of this in living bone, you've got about 15% water, about 30% collagen, that's 45, the remaining 55% or so bone salts, and that's going to vary, it's not very exact there. But in the dry bones, the bones that we're handling in lab, they're not in the living state, so they won't have water in them. They'll be dried bones. So they're about 40% collagen, about 60% of the bone salts, the hydroxyapatite component there. Hydroxyapatite is made of it's calcium phosphate is a major component of the hydroxyapatite, Ca3PO4, 2, that's the calcium phosphate. And then the other portion is a calcium hydroxide, CaOH2. Calcium hydroxide. So these two come together, those two combine in different ways to form a more complex salt of hydroxyapatite. But calcium and phosphorus are important components of the bone and important physiological elements that we are exchanging with the bone. When we talked about mineral storage earlier, these are the two primary minerals of the bone matrix. The collagen component is kind of laid down first in bone formation, and then within that matrix of collagen, the bone cells deposit those bone salts. If you were to take one of these bones that we have in the lab and dissolve all of the bone salts out of it, you'd be left with what's like a rubber bone, like a dog bone kind of thing. Kind of a flimsy and loose structure of collagen. If you were to take one of those bones and instead of removing the salts, you remove the collagen component, then the bone will be extremely brittle and crack up really easily, and wouldn't be nearly as strong, wouldn't have the resilience that we know that most bones have. So the collagen gives it that a little bit of flexibility that makes it resilient. Bone salts will give the hardness in there. So put those two together and you have a typical bone. All right, now we're going to talk about the cell types that are found in bone. We just talked about bone matrix, about the composition of bone matrix. Now we'll talk about cell types. First of all, osteoprogenitor cells are the cells that are the precursor to bone cells. They proliferate in areas of bone formation. Your osteoprogenitor cells. And they will become more, they will divide and produce more cells. Some of those cells will become more osteoprogenitor cells. And some of them will become osteoblast cells. So those are the two possible fates after a cell division of an osteoprogenitor cell. More osteoprogenitors or eventually osteoblast cells. Osteoblast cells are the cells that lay down the bone matrix. So these produce bone matrix. These will no longer divide. They're not going to divide to form more osteoblast cells or other cell types. This is the end of the line. So osteoblasts, after they produce the bone matrix around the cell, they become osteocytes. The cell that is completely encased and surrounded by bone matrix is known as the osteocyte. This is the mature bone cell. It helps to maintain the tissue. So it'll maintain bone tissue. The osteocyte. The final cell type here is not related to these others. So this is kind of a progressive lineage of cells. Osteoblasts are derived from osteoprogenitors, and osteoblasts become osteocytes. So that's all in a line there. Those are descended from one another. Osteoclast cells are a combination of monocyte cells. It's a fusion, a syncytium, so we'll write here a syncytium of monocytes. That form an osteoclast. So it's a bunch of cells that get together and they're all enclosed in one membrane. And these have the function of removing bone matrix from a bone surface. So removal of bone matrix. It's the function of the osteoclast. So it's a large, essentially a phagocytic type cell, huge phagocytic type cell that eats away at that bone matrix. The appearance of an osteoclast, we've seen osteocytes, and osteoblasts is not much different from osteocytes that we've looked at before. But anyway, an osteoclast is a little bit different in its structure and has an interesting shape to it. Let's see if we can also draw this in green. The osteoclast cell has kind of a rounded top to it, and then on the side next to the bone it has a very irregular kind of surface down below. They call it a ruffled border, and inside here there would be multiple nuclei because it's a syncytial cell. But anyway, the osteoclast would have one surface against the bone where it's digesting the bone, removing the bone tissue. I always say these remind me of those scrubbing bubbles in the commercials on television that roam around to clean your bathtub or whatever. So these are on the surface of the bone and they're helping to digest bone material when you need to remove bone material and return some of that bone salts to circulation, or simply remodel the bone, reshape the bone for bone growth. So now we're going to revisit bone histology. We've done this before, but we're going to look at it again. Remember that bone matrix is laid down in layers on the outside of the bone. We call those circumferential lamellae that's around the outside, and then down in the compact bone region we have these haversian systems where we have these concentric circles of lamellae laid down around haversian canals, and in between these haversian systems we have some like filling in lamellae in there that we refer to as interstitial lamellae. So we have those three kinds of lamellae: circumferential, concentric, and interstitial. Now, in this bone, remember that the haversian canals on the inside here are going to contain blood vessels. That's going to be an empty space where blood's passing through the bone. The nutrient supply to the bone comes through those haversian canals. And the haversian system, also known as an osteom, this little bullseye shape that we have on the board here. Now, in here, we know that there are bone cells. We just talked about bone cells. Bone cells found in little cavities, and the cavities are known as the lacunae inside the bone here. And so our bone cells are found inside those lacunae, individual bone cells. So here's a bone cell, here's a bone cell. In the lacunae we have the osteocytes, bone cells. Usually the only thing we see of those when we can see them in a histological slide is the nucleus of the cell in the light microscope. So anyway, we have those. We also have small passages that extend between the blood supply and these cells to give them nutrients. We call those the canaliculi. So we have this network of small tubular passageways from the cells, connecting the cells to other spaces in here. So we have this network of small canals, canaliculi. Small canals, canaliculi, bridging between here. So we have the lamellae, we have the haversian canals and the haversian system surrounding that. We have osteocytes in lacunae and canaliculi going on here. And then we have the spongy bone. And in the spongy bone, we don't have these haversian systems that we have in compact bone. We don't have those layers laid down tightly next to one another. These structures out here, this is often referred to as cancellous bone or trabecular bone or simply spongy bone. Three different names we give to that. And it's made of interconnecting little pieces of bone. We call these either bone spicules or trabeculae that form these little bridging pieces in here. And they are just made of solid bone matrix material. If you cut them in cross section, remember that they will have layers, usually just 2 or 3 layers between the inside and the outside, but the canaliculi will go all through there, and there will be bone cells within that structure there. So no hollow cavity in the middle of that bone spicule. And let's see, there will be the bone lacunae, the bone cells, the osteocytes in there as well, and the nucleus in there. So anyway, it's a cross section through a bone spicule or trabecula. And don't forget that in the spongy bone we have the blood-forming tissues in here. So this would be all full of cells that are dividing to form different kinds of blood cells. Blood-forming tissues, hematopoiesis, hematopoietic tissues. All through here. In the spongy bone, the red marrow, now the tissue that lies against the bone, all through this red marrow, there is a thin layer of collagen in there, and I don't usually make mention of it, but I'll go ahead and mention it now. Covering all the bone spicules going through here, surrounding that. That thin layer of connective tissue is often referred to as an endosteum. Remember that the outside of the bone had a layer of connective tissue called a periosteum, but the red marrow here has its endosteum. In the spongy bone. Anyhow, so that's just a quick review of the histology of bone. Now a word about bone formation, growth, and remodeling. These are 3 different topics really, but first of all, formation. How does the bone become a bone in the first place? It's embryonic development. There are 2 different kinds of processes that lead to the formation of the bones of your body. One of them is known as endochondral bone formation. And in the word endochondral, the chondro you should recognize is referring to cartilage. Most of the bones, the long bones especially in your body, originate as pieces of hyaline cartilage. Developmentally, where they first start to form, they first form as a piece of hyaline cartilage. So you have an early cartilaginous kind of skeleton to form, and then that cartilage is replaced with bone. It starts by forming a layer of bone on the very outside of the cartilage, and then eventually the cartilage to the inside of that bone that's forming around it, some of that cartilage to the inside starts to die, and as it dies, blood vessels move in, and we start to form spongy bone to the inside of the cartilaginous bone. So the endochondral bone formation starts out with a cartilage model. It adds bone to the outside, and then the cartilage inside starts to die, and we replace that with spongy bone on the inside. So that's in form of endochondral bone formation. Like I say, most of the bones of your body begin as cartilage and then are replaced with bone tissue. Next, membrane bone formation. Membrane bone formation begins in dense connective tissue layers, single thin layers of dense connective tissue, and within that dense connective tissue you start to form little osteogenic centers, places where we're going to start to form bone. And it forms as a spongy bone first, and then as these pieces of spongy bone start to connect with one another, underneath that collagen of that surrounds that spongy bone development, we start to form some dense bone. So your spongy bone comes first, and then your compact bone is added afterward, kind of the opposite of what we saw in the cartilage bone formation. But these form just a few flat bones. We usually just think in terms of the bones of the skull here, the flat bones that surround your brain. They're the parts of the frontal, parietal, temporal, and occipital bones primarily when we think of this membrane bone formation, which are jaws also, and your upper jaw as well, forms by membrane bone formation. So those are two different types of bone formation that occur. Bone growth. Bone growth, we have two different kinds of bone growth. After we have the bone fully formed there, we can have what we call epiphyseal growth in a long bone. Like I say, that's pretty much limited to your long bones, where you have an epiphyseal line, and you can add to the length and size of the bone at the epiphyseal line on either end of a developing long bone. Other than that, we have a process called appositional growth. Where we add bone on the outside of a bone. So where that periosteum is on the outside, some of those cells under the periosteum become cells that will form new bone. They become osteoblast cells, osteoblasts that develop into osteocytes as they are surrounded by more bone matrix. And also the blood vessels that are under the periosteum against the bone, they get surrounded by bone to become new Haversian systems within the bone. So we have this appositional growth on the outside to increase the size of the bone. And during all of this, both epiphyseal growth and appositional growth, we have bone remodeling. Remodeling is constantly happening. We're always adding some new bone material and always removing bone material. So we're reshaping the bone, and the bone can be reshaped not only with the growth of the body to accommodate the growth of the body, but also sometimes to accommodate certain pressures. So if you do a lot of weightlifting, you're going to reshape your bone over time so that it's better able to support that. Any kind of pressure or that's exerted on a bone for a long period of time will help that bone to reshape in such a way to accommodate that pressure. That is the principle behind moving the teeth within your jaw when you have braces, when you're doing that orthodontic work. So you're going to push the tooth to one side more than the other side, and the bone is going to completely reshape itself to accommodate that movement of the tooth within there. It just takes a long time to do it. In different parts of your skeleton, you remove and replace bone at different kinds of rates. So some will happen over the course of just a year or two, and other places will take more years for you to completely remove and replace all the bone that was there originally. But it's always in some stage of removal and redeposition of bone, doing that remodeling process in there. So two different kinds of bone formation in the first place when your bone are first forming, either by a cartilage bone formation, endochondral, or replacing a dense connective tissue membrane with bone, membrane bone formation. Two kinds of growth. You can add to the growth of long bones at the epiphysis, where we have a cartilage plate in there that is adding bone to either side. And by the way, that particular kind of growth is essentially the same kind of process that's involved in converting your cartilage to bone in the embryonic stages. Only it happens kind of gradually at that epiphyseal plate to add to the length. And then appositional growth, growing a bone from the outside. But both of these are constantly being remodeled during this process to accommodate the growth of the body and forces that are placed on those bones. So that's bone formation, growth, and remodeling. Now a little bit about bone fractures, since we're often concerned about that topic. When we're talking about bones, we think about people who've broken their bones. First of all, just the simplest kind of bone fracture is simply called a simple fracture. This is a type of closed fracture where the bone simply forms a complete fissure line from one side to the other through the bone. It remains in place and does not protrude through the skin, as opposed to a open fracture, which is a compound fracture. In an open or compound fracture, what's going on here is we have one side of the bone here and the other side of the bone completely displaced and extending through the skin. So if, let's see, the surface of the skin were along here, we would see that bone kind of protrude through the skin. That's your open fracture. It goes all the way through there. So those are the two types of fractures. Sometimes when the fracture occurs, you get lots of pieces to form in between the two broken ends. And when you have that occur, let's kind of draw that in here. So here's one end of the bone here. There's a piece over here on the side. There's another piece down here. So you got all these jagged, crushed pieces in the broken bone in there. And this is what we call a comminuted fracture, comminuted, which is similar to a kind of fracture where you have the two ends kind of impact one another, where they both come in, both ends are moved in. That's and it's usually both comminuted and impacted in there. So you have lots of pieces in the fracture. So those are some of the names applied to different kinds of fracture based on the physical result of the fracture, I guess you would say. It can be either just a simple closed form, or it can be open compound, where the bone is displaced and pushes through the skin. Comminuted, where you see lots of pieces or fragments at the breakage, or it could be impacted, where the two ends come together and are pushed together in the process. Now, there are some kinds of fractures that have special names depending on location. Fracture of the radius at the wrist, for example, or the fibula near the ankle down there, have special names, but these are the general kinds of breakages that you see. Okay, we're going to talk about broken bone repair. We just talked about the different kinds of fractures that you see in bones. Those were all complete fractures. We weren't referring to like hairline fractures and stress fractures, as small cracks that might form in the bone, but here we're talking again about larger fractures, the events that occur to repair a bone that's been broken in one of those ways, like a comminuted or impacted or a simple or compound fractures. So broken bone repair, first step is to form a blood clot, what we call a fracture hematoma. We'll go ahead and number these steps. So that's step one, formation of a blood clot around the area of damage of the tissue. Next, in that area around all those broken pieces of bone, we want to get rid of that damaged tissue. So there's a phagocytic removal of things. Phagocytic removal of the damaged tissues. That's mainly by neutrophils and monocytes, our primary phagocytic cells in the tissues, in the connective tissues. So, blood clot forms. In that blood clot, we move in some phagocytic cells, remove the dead tissue, and most of the clot in the process. Let's see, next we need to move some blood vessels in there to help us with the repair process. We're going to call this the investment of blood vessels. So we need to have a blood supply there for the reconstruction of the broken bone. Next, we form, in that area where we need to repair, we start forming some fibrocartilage, what we call a fibrocartilage callus. Fibrocartilage callus formation. So we're going to build back some connective tissue, some cartilaginous connective tissue in there that has a fair amount of collagen fiber in it. So that's going to be our starts to solidify that broken area of the bone with fibrocartilage. We'll eventually need to replace that with spongy bone. That'll be the next step. Put spongy bone in there, and at that stage it's pretty well stabilized. Typically when we get that callus, we start replacing that callus with our spongy bone, but it's still not quite as solid as it was before it was broken. So we're going to do some more rearranging of things. What we're going to do is remodel the bone. And on the outside of the bone, we're going to add that compact bone. To make it as strong or stronger than it was before. Get that back to what we need in the process. So these are 6 steps involved in healing up a broken bone. Form the hematoma, remove the damaged tissues, put blood vessels in there to get things started, the healing process. In that, we're going to have, in that healing process, we'll bring in fibrocartilage, start to form fibrocartilage. It forms a callus, kind of a intermediate stage of tissue development there. And that callus then will be replaced with spongy bone, and then finally we'll remodel all that bone and put our compact bone on the outside. So that's the healing process for a broken bone. Now we're going to talk about factors affecting growth and loss of bone growth and bone loss. First of all, we have a list here: minerals, vitamins, exercise, aging, illness. There may be other things. If you're taking some kind of medication, for example, that would kind of relate to illness. So your medications may affect bone growth as well. Minerals, we already know that the primary composition of bone is made of a calcium phosphate bone salt thing. But in addition to calcium and phosphate, calcium, PO4, magnesium, and fluoride are also important minerals in maintaining healthy bones. Vitamins, there's a whole list of vitamins. Let's see if I can put some up there. I know A, D, vitamin K. Let's see, I'll check on a couple of others. Vitamin C and vitamin B12 are also important vitamins in the physiological processes that lead to bone development, the laying down of bone. All of those can be useful. Exercise is another thing that's going to be important in maintaining our bones. We already talked about bone remodeling and how pressures on the bone, stresses on the bone will help to determine how a bone is remodeled and affect bone growth in that way. Aging, we're all familiar with osteoporosis, the weakening of the bone, the making of brittle or more brittle bones in people as they age. So that's an important part. I didn't include in here hormones. That should have been part of my list, right? So after vitamins, I should put in here hormones. Hormones, another thing that affects bone growth and development. Human growth hormone, is one. Insulin-like growth factors. Thyroid hormones. Testosterone and estrogen, the sex hormones. And then two very important hormones in regulating blood calcium levels. So you take away from your bone or you add calcium to your bone. Calcitonin and parathyroid hormone. So anyway, several hormones are going to affect that. I can't believe I left that out of there when I first put it up there. So we have these minerals, calcium phosphate groups, magnesium fluoride, vitamins A, B, K, C, B12, these hormones, human growth hormone, insulin-like growth hormone, thyroid hormone, testosterone, estrogen, calcitonin, and parathyroid. Exercise, obviously important, like we mentioned. And then aging, osteoporosis is a problem with age. Other things about just being more sedentary, other kinds of conditions, often having to do with illnesses. So illnesses and overall weakened body, lack of nutrients or whatever. Lots of things can lead to bone loss or bone weakness because of illnesses and poor health overall. So these are some factors that affect bone growth. You need to probably know this list, at least, of those 6 things: minerals, vitamins, hormones, exercise, aging, and illness.